Uh, Hello, everybody. Now, today's lecture is about actually coding in MATLAB and some control theory aspects. For example, we have the Root-locus plot. We are going to examine it further and think about the algorithm that can be used to generate a Root-locus plot, because we have already the R-locus command in the control system toolbox. But what if we want to code it ourselves? The same goes for the Bode graph. We have, again, a Bode function which generates us the Bode plot for certain transfer functions. But how can we code it ourselves? That is going to be the question here. And of course, if we want to have a simulation, for example, if we want to apply different types of inputs to a system, how can we do it without using any simulating or graphical user interface whatsoever? Just use the step function that is available. How can we do that? Is there a trick? That will be today's discussion. Now, let's actually start from the Root-locus. When you define a transfer function, let me quickly demonstrate it to you. Let's say we have a transfer function like this. We have the R-locus command, which generates us basically the Root-locus plot. Now, first of all, what is the Root-locus plot? How can we use this Root-locus plot? What does it tell us? Or why is it useful? Now, let me first of all add another part to it so we have a more exciting one. Maybe this one. So now in control theory, what we are going to touch base up on in this course in the upcoming lessons, we want to change behavior of systems. For example, we have a transfer function, and this transfer function is actually representing a dynamic system, but it uses the Laplace domain to do that. We have the S variable, which is in the Laplace domain. It is actually a differential equation, but we look at it in the S domain, which is basically a fraction of polynomials. So that's that. And if we apply certain inputs to these types of transfer functions or dynamic systems, they will have two basic responses. One of them is called the transient response, which is, as the name implies, transient. It will fade away. It will have some effects because it's a dynamic system, but they will fade out. And then we have the steady state, which means that the system is at rest. So these are the portions of a response that we can observe in a transfer function or system, a dynamic system. Now, we most of the time use linear and time invariant systems. For example, here we can see it's a linear system because if we write down GS, you'll see the polynomials are polynomials. And in fact, it is a linear system because you can obtain the corresponding differential equation. And for those who want to know what the differential equation would look like, what we can do is we can just transition based on this fraction here. Let me quickly show you. So this is the fraction. This is equal to y divided by u. So if we multiply everything, so this should be actually y divided by u. So this is equal to y divided by u. Because it's the input-output relation, a transfer function has an input and an output, and the relation between that is given here. So it would be u equals y times this polynomial. So let's say y times this equals u. And since we are in the Laplace domain, I can just distribute y here. So s cubed y plus 5s squared y and 9sy plus 9 equals u. Now, since we are in the Laplace domain, if we multiply with s, that would correspond to basically using the derivative or taking the derivative. So L, the Laplace representation of d divided by dt is by multiplying with s. So it means that this would be the third derivative of y, and since here we have s squared, it would be the second derivative, just the derivative, and itself equals u. So as you can see, this polynomial, this characteristic polynomial, or the denominator of the transfer function, can actually be used to directly obtain the differential equation. So we're basically concerned with these types of differential equations or dynamic systems, but what we do is we just apply a change in the input, a change in the scalar. So we use step type inputs. So a step type input is basically the following. It just goes up like this. So it's this type of change because it was at rest here, 0, for example. And it changes its value to, let's say, 1. So this is basically the step function that we use most of the time, and we see what really goes on in the system, or what how the system responds. So and sometimes in the transients of the system during this change, when it's not at rest, what we observe is we observe some statistics about the response. For example, we have the settling time, which means that how much it will take to transition from the transients to the steady state. We have overshoot, which means that we applied 1 unit of input, and how did it exceed the input? Did it not? So we're basically trying to track that using the overshoot. So we look at its steady state value. Is it reaching it? Is it surpassing it? That's going to be the amount of overshoot. If not, then the overshoot will be 0, for example. We have the rise time, which is basically defined as the time that takes the response from to rise from the 10% of its actual value to the 90% of its value. So the amount of time that is necessary here is basically this. We have peak time, which is basically the time instant where the maximum occurs, etc., etc. And this is basically used to quantify on the behavior of the system. And for some cases, we want to change the behavior of the system. Therefore, we have to change the overall system. And how can we do that? Well, basically, we most of the time use controllers for this. And using a unit feedback loop like here, we try to get the best result that suits us in terms of changing the behavior. And here we have this dynamic system, or the differential equation. We have k, which is a scalar, which is a controller, but it's scalar, and this feedback structure. Now, if we look closer to it, we can see that we can give the signals some names like this. And by the way, we have a minus sign here. So this is minus y here. So r minus y is equal to e. So that's one of the equations that we have. And then u equals k times e. And y equals gs times u. Now, we set up this feedback loop. We choose, or we try to choose, a controller k, so that, for example, the overshoot changes, the settling time changes. That's basically our aim here. And we can use the Root-locus plot, this plot here, in order to come up with suitable, hopefully suitable k values. And the thing that we see here is basically the closed loop poles, and we start at the open loop poles. And before I transition into that pole stuff here, we can actually work our way out with these equations here. If you don't know how to deal with a unit feedback loop, you can just name the signals, use the identities, and try to solve it. For example, we have y equals gs times u, but we know that u is equal to k times e. So let's plug it in. So this is basically, let me just change the order here, k times gs times e, which makes sense because we start here, multiply it with k, multiply it with gs, and we have the output. But we know that e is not independent of r and y because the difference here, r minus y, gives us e. So let's plug in again. This is basically our equation here. Now, if we distribute this factor here, it would look like this. And you can see we have y here and on the left. So let's combine them. It would look like this. If I just factor out y here, this would be 1. And there we go. We would get this. Now, the only thing that remains here is to divide everything into this factor here. That would look like this times r, but of course we are just going to place r on the left hand side and we're good to go. Now, why did we do that? Well, basically, if we are interested in the open loop transfer function, we can see that the open loop transfer function is a relation between input u and output y. So the fraction y divided by u will give us gs. In this case, when we place a controller and the unit feedback loop here, we see that our actual input is not u anymore because it is determined by k times e, and e depends on r minus y. But our actual input, where we will apply the step type input, for example, will be r. So our input is r, but our output is still the same, y. So the fraction between y and r should give us the transfer function of this whole thing here, which is called the closed loop because we have placed a loop and we closed kind of the loop here. So it's called closed loop. Our closed loop transfer function looks like this. Now we try to come up with sensible k values that help us in changing the behavior of the system. But in order to determine its behavior, we use the poles of a system. In this case, we have -3 here and the roots of this one here. So let me show it to you. It is basically -1 plus -1.41. These are the two loops, the two poles, and the third one is 3. Now, for some reason, we want to change them. And we can see that one is at -3 here, and two of them are complex conjugate pairs, forming a complex conjugate pair. And we can see now that if we increase k, starting from 0 to infinity, the pole on the left here, -3, will get further away, will move to the left. Whereas the pair here, they move kind of on this path here. One of them goes on this path, this branch, the other one on this. And at some point, we reach actually the point of danger, which is basically the j omega axis. Because we know that if the poles are on the left-hand side, then we will get stable behavior here, which means that it will not tend to infinity. If it's not stable, you'll see that it will tend to infinity. And we are going to see if it's going to do that or not. So I can actually click and see what the value is. For example, if I use 52, so if I use k equals 52, that will cause some problems. And if I, for example, plug in 17, that will have no problem at all. So before I do the whole thing here, let me just go ahead and calculate the transfer function here. It was k times gs divided by 1 plus k times gs. We don't really have to do this. We have a feedback command which can do the same, which asks us for the feed-forward path, so the multiplication of this, and the feedback path, which is just 1 because it's a unit feedback. structure here. And the minus sign is included by default. If you have a plus sign here, you should provide a minus sign here. So this is basically the same. So I'm going to use this one here. So let's try this for that. And let's look at its poles and zeros. And let's repeat it for the value 17 here. So now we can see that we have basically the value 52 here. And okay, so there are too many transfer functions. So that looks better. Now, yeah. Okay, that's better. Now, if we use k equals 52, we can see that we have a minus sign here. That would indicate that one of the roots, or even both of the roots of this polynomial, are on the right half plane. And here, that's not really happening. We have a s plus 4, 3, 1, 1, and s squared plus this polynomial, which seems to be stable. And we can quickly check if it's the case or not by plugging in these values here. Get rid of s, plug in 1, and you can see there are positive values. So it would be on the right half plane. Now, if we want to be sure, what we can do is we can just use the step response here. Let's have figure 1, step response, figure 2, step response, and see what's really going on. So you can see the difference here. This one is unstable, meaning that it will oscillate and the oscillations will grow. It will tend to infinity, and you see there's a huge value on the y-axis. Whereas the other one, the lower k value here, has a whole different behavior, but it is still stable, meaning that this portion here is the transience of this system response, and here somewhere we settle down and we are switching to the steady state where everything is basically not moving at all. So this is the part where it's moving, where here it is at standstill. Now you can also combine the before-after step responses. Before we had GS, now we have this red plot here. Let me just quickly repeat it. If you want to compare it, you can see the step response looked like this. It behaved totally different than it behaves now. I would, of course, argue if it's a good change or not, because it is oscillating too much. And yeah, this one did not oscillate that much. Maybe the system is not a good candidate for control or using this Root-locus plot to control the system. But it depends. Maybe you're looking for something that should have this many oscillations. I don't know. So yeah, but you can see the behavior changes, and we do it by just choosing a scalar value k in a unit feedback loop. So this is basically the most basic controller that you can design, because the controller itself is just a scalar, meaning that it is static. It has no dynamics, no differential equations associated to it, because it's just a number, scalar. So our Root-locus plot is therefore really important. And if we want to generate the Root-locus plot ourselves, what do we have to do? Well, let me just get rid of this whole thing here, and let us look back at the Root-locus plot here. So this is the Root-locus plot, and we know that these points here are basically denoting the open loop poles. And then if we increase k from 0 to infinity, because this is called the positive Root-locus, we see that, for example, for certain gain value 1.82, this pole here moves from -3 to -3.26. And we can also see the same effect here. If I can just click on 182, which is sometimes really hard, approximately 180 something, so it's also close enough. We can see that basically the system will look like this for this gain value here. So the algorithm here, of course, there are two basic approaches to this. One of them is using the theoretical method. So we have some Root-locus rules, which you might remember from your previous lectures or semesters. You look at the order of the system, the amount of poles, the amount of zeros, the difference. You calculate the asymptotes, the intersection of the asymptotes, and then you determine lots of stuff in order to continue with the plot, and you generate the plot, the sketch, the Root-locus sketch by hand, and you're good to go. But we're not going to take that approach because we have MATLAB and computational power at hand. So what we can also do is take a different approach, which is far easier in terms of rules. And it is the following. You have to determine the poles of the closed loop here. We know how to calculate the closed loop. So we saw that, for example, if we want to use the symbolic toolbox, we can use this expression, which I already have derived. So we can use this relation here. So if we would have chosen a certain k value, at that point, we could get the closed loop transfer function. And then we're interested in basically its denominator or the characteristic polynomial. So we can use num then, PSS, and we would end up in PCS, which is the characteristic polynomial. It would depend on S, of course, but also on K because we have chosen a certain K value. So at this point, what we can do is we can just use maybe solve in order to solve the roots. So this should be equal to 0. So what we can do is we can solve this. But what we want to solve is basically S. That could be one of the approach that we could take, or we can take the coefficients of PCS, all the S coefficients, and look for its roots. I have already used the roots function. Here, roots. If you provide it 1 to 1, it is -1 and -1, which is obvious. So you provide the coefficients of a polynomial to the roots function, and it will immediately calculate the roots of this polynomial. Or you can just directly solve it by equating it to 0 and choosing the variable s in order to solve it. So it is basically possible to use both of them. So yeah, I'm just going to go with this approach here. First of all, by the way, we don't have the symbolic representation. So let's use the symbolic representation here. S squared plus 2 times S plus 3 times S plus 3. So we have that. Of course, we don't have K. So what we can do is we can just go ahead and define a K vector. Let's start from 0 with 0.1 steps to 0.4. And at this point, we need to basically choose one of the K values, plug it in, look for the roots, and plot the roots. So it's going to be a plot. Let's create a figure for that. Figure 1, for example. And let's also use hold on to plot on top of each other. And of course, we will use a for loop for I equals 1 to length of kvec. We will repeat this for every k value, basically. So that's the reason why I do this. And k should be equal to kvec, the ith element of this vector. And that is pretty much it for now. Let me just run it to see what the roots are. Yeah. First of all, let's convert everything into double, because you can see you get the symbolic expressions for them, but we're not really interested in the symbolic expression. We are just interested in the value. When I rerun it again, you can see, of course, for k equals 0, it kind of gets rid of the whole polynomial thing. So maybe we should leave it out because it just gets an empty double column vector, which is basically empty stuff. So let's run it. And now we can see we have basically, depending upon the order of the transfer function that we are interested in, we have that many rows in terms of roots. We can see one of them is minus 3 point something, and then the other one is close to the open loop, and it moves slowly away from the initial point. And if we increase this vector, it will just get further apart. The only thing that is left here is to, let me save it to poles equals this. The only thing remaining now is the representation. So what we should do is we should plot them on the S domain. Now, since we're dealing with the S domain, I can just write down X label and call it sigma, and Y label J omega. So, but if you want to be fancy, what you can do in MATLAB is you can just provide a backslash here if this is a symbol that is already defined. Sigma is a special character here, a symbol, so I can just put in the backslash, so it will go ahead and look it up and just use that one. You might also want to go ahead and use alpha, beta, delta, gamma, whatsoever. So it's possible. So sigma is one of them. And instead of having this omega like W, we can also use omega like this. So it's just a fancy way of writing it, nothing more. Let's call it the Root-locus plot, so something like that. Now, of course, this indicates the fact that we need to calculate the real part of the poles, use it for the x-axis, and the imaginary part for the y-axis. So it's important to note that. And, well, actually, it is kind of a Cartesian coordinate thing. So we're just going to use plot and then take the real part of poles. So we can use this real function here on poles. And the last one, if it's defined or not. Oh, we didn't run it. Do we have k? Yeah, let me just go ahead and run this part here. So poles, and the real part of poles is basically this here. So I'm providing the real part for the x-axis, and what I can do is I can also choose the imaginary part. It will give me the imaginary part. So you can see this is pure real, the other one is not. Of course, what we need to do is we need to place some crosses or X's because, well, poles are denoted with crosses and zeros are with circles. I can also increase the line width maybe. And we should be good to go, I guess. Now we need to increase the vector, so maybe we should go up to 10. It takes quite some time because we are looping through each element of this vector. And if you look at the length of kvec, you will see it has 100 elements. So you'll repeat this thing 100 times. So it will take more and more time if you increase the k value, the upper limit of the k vector. So you might argue that this doesn't really look like a Root-locus plot because it is kind of a discrete Root-locus plot. So we are just changing the k value. We don't connect the lines. We have just crosses and they form the shape of the Root-locus that we've seen originally. Of course, we can fix that. We need to think about it a little bit and we should be able to fix it. So, and for that, what I can suggest is the following. For each k value, we will have 3 rows. We've seen that for each k value, this will be basically the outcome. So we can align all the results with the k values using a matrix here. That would have 3 rows based upon the order of the system and as many columns as the vector length kvec. So I can go ahead and generate something like this, like poles, and then just use zeros as a function to generate zeros. And then, well, basically 3 because a third order system, and length of KVAC because that many columns are necessary. Then what we have to do is, instead of plotting it here, we have to assign it accordingly. So all the rows, I take all the rows, you can also go ahead and do it like this, from 1 to 3. I want to set up the ith column because the ith element of KVAC is used and the ith column will correspond to that. So if I do this and run it again, of course, we will lose the plot here. It will not plot. And if I look at the elements, the first 5 columns, for example, you can see that basically the first pole now lives on the first row. And if I want to plot a continuous path for this pole, I can use this row here. So use row 1, plot it, and it will be a continuous path. It will start from -3 and it will go to the left. You can observe that from here. And for the next pole, I can use this one here. For the next one, this one. So I can just create a little for loop here that goes through each row and plots them using different colors. So that would be the Root-locus plot, and I'm going to do that. But what I really did was I just used the value 0.1 for the first column here, 0.2 for the second column, 0.3, 0.4, 0.5, etc. So it goes on like that. Now what we can do is we can just come up with a for loop from 1 to 3 and just plot the whole the real part of poles, but the first row. Basically, this is the only thing that we need to take into account. So if I just take the first row, you can see this would be the first pole. This is the second one. This is the third one. And that's basically it. So I'm doing the same here. Of course, not the first 5, just all of them. A column stands for all the elements here. And just give it a line width of 2. And we're good to go, I guess. Of course, we have to place the imaginary part too, instead of that. Let's run it and see what happens. Yeah, we have to use the ith element here. My bad. Let's see. There we go. At least it looks more like a continuous plot. But of course, the open loop poles are missing because we know that exactly at -3, we should have a pole and there's nothing. It's just somewhere off here because we have used 0.1 as the first value and not 0 here. Therefore, what we can do is we can just calculate the whole, the open loop poles here, and we can do it by just using numDan, and then we have the numerator and denominator, DSS. And of course, what we can do is we can just plot the real values of, or we should just calculate the zeros. So zeros equals double roots coefficients. I'm just basically repeating this step here. This is basically the same. Instead of writing it down, I can just copy and paste it. And here we will use the numerator. So get all the S coefficients of the numerator, look for the roots, convert it into a double, and you have the zeros here. And let's do the same for the poles, but this time the denominator. And we're just going to plot the real value of the zeros. Even though we don't have any, I'm just going to plot it here using a black X and line width of 2. Let's repeat the same for the poles. Since the zeros are circles, the poles are crosses, this should do the trick. Before I go on, I am not really happy with the k vector that I create here because it takes quite some time to calculate the whole thing. So instead of using this linear step approach, what I can do is, by the way, I can use it using linspace, which is a function, takes the starting point and end point and number of points. So this is also possible. So if I do this, you will see that kvec looks like this or like this. So it starts from 0, has a linear step size and ends in 100. But I can change it to log space so that I start at -2, so 10 to the power of -2, 10 to the power of 2 with 100 points. So, of course, it's not the best, but still it is something. It increases the step. So, now this looks more convincing, if you ask me, and we can see that we have the j omega axis here somewhere. And if we change the system, by the way, what I can do is I can also automatically calculate the order of the system here. Let's call it n. And I can do it by looking at the length of the coefs vector here, because let me show you what the coefs vector gives me. It gives me the coefficient vector of the denominator of a system. So if I look at the length of the denominator of the system, the coefficients, I can see that this is s to the power of 0, s to the power of 1, s to the power of 2, s to the power of 3. So the length is 4, but the order is 3 because we have a constant value. So it means that I can look at the length of this and subtract 1. So this would be the order. And if that's the case, I'm just going to place an n here in order to be able to adapt here. And of course, this is not really necessary. I can just do it the whole thing here. And yeah, I guess we are good to go. Let us run it again. It still takes some time, but it shouldn't actually. But yeah. So then the good thing about this is that if I change the transfer function, for example, if I add a 0 to it, it should change the whole Root-locus plot here. Let's see. There we go. You can see it is basically the Root-locus plot. The colors are a bit off, but not really that problematic. We have a 0 here, we have a pole here. This pole goes to the 0, 2 poles are here, and they just go away here. So if I want to speed it up, I can just go ahead and do this. It should speed up a little bit, at least. But this is basically the Root-locus plot here. And let me also remind you of the fact that our characteristic polynomial is actually 1 times k GSS, because the whole thing was k times GS divided by 1 plus k GS. So in this case, if we look at the Root-locus plot, we're interested in this equation given in line 32. So it's 1 plus k times GSS. Now, if I want to change it to ns divided by ds, which is the numerator of the open loop transfer function and the denominator of the open loop transfer function gs, then I can see that I can conclude stuff about this. For example, since this equation has a fraction in it, what I can do is I can multiply everything with ds. and it will change into this equation here. Now, if you look closer, and if you plug in k equals 0, for example, k equals 0 into this equation here, you can see that this term here will vanish, and we will get ds equals 0. So ds is the denominator, therefore it will be the roots of ds, and therefore we will see the poles. So these will be the poles of the system, and of course the open loop poles, because ds is the denominator of the open loop transfer function. By definition, we said that gs is ns divided by ds. So therefore, we have the open loop poles. That's the reason why if we plug in k equals 0, we get the open loop poles, because this is the equation that we are interested in, and there's a fraction. If you multiply with ds, you get this. If you plug in k equals 0, this vanishes, and ds equals 0. Now, let's say k tends to infinity. Now, this is a bit more tricky, but yeah, if k tends to infinity, one way of viewing this would be to say that k grows more and more, and if it does, then ns will become more relevant, and ds will shrink compared to ns. So therefore, ds would vanish, and yeah, that's basically it. But instead of looking at it like that, we can just divide by k. So ds divided by k, ns will stand there. And if k goes to infinity, you'll see that this term here will vanish, and we will get ns equals 0, which are the open loop zeros here. So this is the reason why, when we talk about the positive root-locus, that the poles start at the open loop poles and end in the open loop zeros. So we go from poles to zeros if we have a root-locus plot. That's the reason why this pole here actually tends to the 0 here. What about the other ones? Well, if the system has just one 0 in this case, all the other zeros are just assumed to be at infinity. So this 0 is at j infinity, the other one is at minus j infinity, so they will still reach them theoretically. So this is basically the code. Let me just get rid of this part. This is basically the code using the symbolic toolbox in order to generate the same root-locus plot numerically, in this case, of course. So that's one thing. Knowing the background of root-locus is important in terms of understanding about systems and root-locus plots, all that sort of things. Now, this was our first task. Now, the second task is about the Bode graph. And it's also another important thing. So let's just create another file here. Let's have gs equals, let's say, tf1 divided by 1, 2 times 0.707 times 1 plus 1 squared. So I'm just writing it down, but I might go ahead and change it later. So that's the reason why. So let's run this one. Let's see what's happening here. And you get this sort of plot that is quite interesting and tells something, but which is not really that obvious at the moment. Because one of the things about the Bode plot is that we have angle degrees here in units, but here we have decibels, and then there's this weird spacing policy. You can see that it starts from 10 to the power of -2, 10 to the power of -1. This is basically omega equals 1. The x-axis is frequency, radians per second, which is omega. And then we have 10, 100, etc., etc. So first of all, this is a logarithmic plot. That might be one of the setbacks of this if you're not familiar with the Bode plot. And then you have this decibel, and you have to know what 0 decibel is, etc., etc. Now, since we have the name frequency, we can already assume that Bode plot is a frequency plot. And again, since we are dealing with the Laplace domain using transfer functions, let me just write down what GS is at the moment. So 1 divided by S squared plus 1.414 times S plus 1. So this is our system. Now, an important identity or relation is the relation between the Laplace transform and the Fourier transform. So there's a relation there. And if you look at the Laplace integral and the Fourier integral, which is basically the transitioning from the time domain into the frequency domain, if you look at those integrals, what you might see is that in the Laplace domain, we will use S, but if we want to transition from Laplace to Fourier, what we can do is we can just plug in S equals j omega. So it is basically the Laplace domain is basically a transform, but the Fourier domain is basically a projection of that whole transform. And that projection happens at S equals j omega. So I'm not going to go too much further into the mathematics and the whole theoretical part, but this is important. You have to know that the Fourier transform is basically a projection S equals j omega, and it is still the same. So if we deal with Laplace, if we plug in S equals j omega, we will immediately get the Fourier transform. So we are going to do that and see what really happens here to this system. So let me define omega, the frequency variable here, which is 2 pi f or 2 pi divided by t. And let's have j omega because we plugged in S equals j omega. Let's use substitute. GSS S equals 1i times omega. Of course, nothing magical will happen here. You'll see just something that looks like this. And if we want to be a little bit fancy about this, what we can do is we can just use pretty to prettify the output. And there we go. That's basically it. Now, this might not look that powerful, but keep in mind that this is basically just a functional fraction, which depends on omega and is a complex number. So it is a complex valued function depending on omega. Now, in the frequency domain, we don't really look at stuff in control system theory, at least. In terms of complex numbers, we're not really interested in the Cartesian coordinates most of the time. Instead of doing that, we look at the polar coordinates most of the time. So we need to look at the absolute value of this and also the angle of this. So we are going to transition from the Cartesian coordinates into the polar coordinates immediately, because we will want to get rid of the imaginary parts. So therefore, we will have basically the magnitude of this and also the phase of this. So how can we transition into that? Well, we can get the real part of j omega. Let's call it A. We can also get the imaginary part of that. Let's call it B, because A plus BI. So let's look what A and B look like. They look like this. Of course, it's not really pretty, but yeah, it is what it is. So what we can do and what the Bode plot does is basically the following. Of course, we know that we can calculate a squared plus b squared square root in order to come up with the absolute value, which is going to be the absolute value here. We can also take the a10 of b divided by a in order to look at the angle. And if you want to use the degrees, you have to append the letter d, which stands for degrees. So if you use MATLAB, you can just go with degrees. So the sine of 30 degrees, if you sine d, it's going to be 0.5, it will be correct. But if you don't do that, you will end up in a different answer, which is not correct at all. This is in radians, but if you want to use degrees, you have to use d. We can use this for the absolute value and this for the angle value of this for a certain omega value, but they are still depending on omega. So the Bode plot just creates a vector for omega, let's say omega vec, and let's start at 0.1, increase with 0.1 up to, let's say, 0.5. So what we can do is we can plug in each omega value into the absolute value, the magnitude, and the phase, and see what happens. And the Bode plot just combines them as two plots and shows you the result as a plot and nothing more. So let's recreate that. Let's do that too. I'm going to just use I equals 1 up to the length of omega vec. And now at this point, I will have the magnitude here, zeros, size of omega vec. If you want to copy a certain vector with all zeros, you can just use zeros and then use the size of the vector, and it will create an empty copy of the same size. I also want to look at the phase, so let's repeat that. Now, the ith value of magnitude will be the following. We already have this and this, but we have to basically substitute these values. So let's say a val, let's call it double. Let's substitute into a instead of omega, omega val. And that omega value will be determined here. Omega val is the ith element of omega vec. So I'm going to do it for the real imaginary parts. And then I can just use this square root of a squared plus a val squared plus b val squared. So let me show you the result here. So this is magnitude. This is omega vec. You can see that if omega vec, if the omega value is 0.1, we start with 1.4. And as omega increases, the magnitude decreases. We can repeat this for the angle data too. So instead of that, let's have phase, A tan D, and then B val divided by A val. So the phase value 45, 45, 45, it's just going 45 like this. By the way, as far as I remember, there should be something called A tan to D. Yeah, which gives us a 4-quadrant inverse tangent instead of a 1-quadrant one. And it makes a big difference because you have to look at the sine of the real part, sine of the imaginary part in order to determine its quadrant to come up with the actual angle data here. So I'm going to use A tan D and B val comma A val, which should be more correct in this case. So phase, let me run it again. If it's the same phase, I'm going to be okay with that. Yeah, seems to be it. Now, of course, the only thing that remains here is to plot the data by aligning the omega values here. So, by the way, we can see that A val and B val are just values. So it's 0.7 plus 0.7 j, basically. If we plug in s equals j omega and omega equals the last value here, 0.5. So let's create a figure, but we need to use subplot in this case, 2 rows, 1 column, and the first one of that, let's have also, hold on. Let's plot the omega vec and the magnitude. So let's see. So this is basically going to be the plot that we generate here. Let us repeat it for the phase plot. Let's have grid on. Of course, the X label would be omega, and then the Y label would be, for example, J omega. And maybe the argument here instead of the absolute value. Of course, you can also go ahead and use absolute value here. Just plug in the complex value. We have something like this, abs 1 plus 1 times 1i. You can just get the absolute value of that, which is 1 squared, the square root of 2, 1.41. So you can also go ahead and use that. We have also something called angle here, as far as I know. 1 plus 1i just gives us the angle here. Do we have angle D? I'm not sure. No, we don't. So you have to use angle times 180 divided by pi in order to get 45 degrees. So that's basically it. Now, let me increase the line width a little bit, and then also maybe the omega vector too. Now, we already saw that the omega vector was logarithmically spaced. So we can do that too, use log space, as it was the case for the root locus. Maybe just 40, have a lesser value for more performance. And let's see. So there we go. Now, you might argue that it doesn't really look correct here in this case. And I'm not sure why there is a jump now, but yeah. First of all, you can see that the x-axis values are still linearly spaced. And in the Bode plot, that was not the case. We had a logarithmic scale. In order to do that, we can just go ahead and set the value of x scale, the x-axis scaling, to log. So it will just look like a Bode plot. So usually you can just use get GCA x scale in order to look what the scaling in the x-axis is, and you can see that it is linear. But our values are logarithmic, but the plot does not look logarithmic. So therefore, you can just change it to log in order to have the Bode plot effect. Here, the set get function is kind of a more advanced function. Therefore, we have this interesting way of using it. We have GCA, which is the get current axis or clear axis. Here we have get current axis. It looks for the property x scale and changes the value to log here. Now, we did update it here. Oh, we have A here. So that was the error here. It looked a little bit weird. Now it will hopefully update it. There we go. That's better. Now you can see this is basically, again, the Bode plot. The only thing that is missing here, and which we can also still update here, is that we need to calculate the decibel version of this. You have to take the 20 log base in order to convert this into a logarithmic or into decibel. So you have to just plot 20 times log, and as far as I know, it should be log 10, a 10 base log here. If we update it like that, what did we do here? In line 4, Bode. Why is it still open? I don't know. There we go. Now we have this 0 here. So these are now in decibel. This is in degrees. So it is basically the same plot here. And if you want to compare, what we can do is we can just go ahead and create it in figure 2. So there we go. It is basically the same plot. Do we have the same values here? Yep. So it should be basically the same here if you compare it side by side. Now we have generated the Bode plot, but we didn't talk about its usage. We just talked about the fact that if we have the Laplace domain, plug in s equals j omega, it's going to be a projection and you're in the Fourier domain. If we want to talk about the plot itself, we can see, and let me just omit this 20 log thing in order to be, in order to have a better explanation here. Now we can see the following. If you are familiar with the Fourier transform, it is about sinusoidal waves. And we assume that our input has a certain frequency assigned to it. So what we can do is we can talk about sine omega times t. And if you pick a value from the omega on omega axis or the x-axis of this plot, you can see that there are values like 10 to the power of -2. So it's going to be 0.01 or 0.1, or still somewhere around 1 or 2, as the frequency here is still choosable. Let's choose 0.1. If we apply a sine wave 0.1, so sine 0.1 t, omega t, then if we apply this to the transfer function that we have here, by the way, then we can see that the gain of this sine wave will not change, or the magnitude of this will not change. So basically, if we apply the sine wave to a linear system, GS, we will still have sine, so 1 or approximately 1, let's call it 999, something like this would be the gain of it. And if you know a little bit about frequency domain, you know that if the source does not change, the frequency will never change. So this is still the same. But since we have also the phase plot here, the amount of change in the phase here will be, let's click on it and see what it is going to be. Let's drag it here. If we have 0.1, it is minus 8.6 degrees. So it would look like this, minus 8.6 degrees. So that's basically it. Now, looking at the Bode plot, we can basically estimate what the output will look like. Based on the frequency, we get a magnitude and a phase value. Applying that to the sine wave, we can just see what the output looks like. But let me remind you of the fact that this holds only for steady state. So what I mean by that is the following. In the first question, we talked about the step function. If we apply step to a certain transfer function, it will have the transient response plus steady state response. So if you remember the switching questions about differential equations, that was basically the same. So there's a steady state and a transient part. The Bode plot does not hold for the transients of, or the transient response. You should wait until the whole response is in steady state, then it would hold. So if we apply, and I can show you that, let me just generate a t vector 0, 0.1 up to, let's say, 10 seconds. And let's have an input of sine 0.1 t. Yeah, we can get rid of that. And then we have something called LSIM, GS, U and T. So maybe the transpose, I'm always messing this up. Y, comma, T. Let's hope that it works. Let's see. Yeah, it did. So what I can do is I can just generate another plot, figure 2, actually 3. and plot t comma y with line width 2 and maybe a different color, let's say blue. And I can also plot the input in black so we can compare what's really going on. So of course we need a little bit more time. So let me just hold on, grid on, increase the amount of time. So maybe 100 seconds, I don't know. Because it is low frequency, it takes time. You can see there's just a slight difference, minus 8.6 degrees, in fact, probably. And the gain value did not change that much. But here it's not really obvious, but let me just choose another frequency from this plot. Maybe omega equals 1 because it has a drastic change there. So if we change it to 10 seconds and omega is equal to 1, and that should be it, I guess. So you can see now we need a little bit more time, maybe 50 seconds. So there we go. Now here we have chosen 1. You can see that the gain here drops a little bit, the magnitude drops a little bit, and we have, if we even increase it a little bit, it's almost like a cosine. It becomes more of a cosine than a sine, but yeah, it is just shifted a little bit. And if we go to a even higher frequency, let's have 10 seconds now, but let's go to frequency 10. Based on the Bode plot, I can say that it will be rejected because, yeah, 10, the gain value drops to 0 approximately. So that's called now rejecting at this point. And you can see, yeah, there we have a sinusoidal wave, and you can also see the transient effect because it just overshoots, it does some stuff, but eventually it goes down to the steady state here, and we can see it's almost 0. If it's a real world application and you measure this as a sine wave, the blue one here, it's basically going to be noise and nothing else. So you can see that the Root-locus was for a controller design thing. The Bode plot here is more of a system identification tool. You can see and judge the system based upon this plot here. You can say, okay, there's a certain gain. I can see which frequencies will have gain what and which frequencies will have a lower gain, maybe 0 at this point. So you can see that these frequencies pass. Actually, these are rejected, and you can just conclude that this is a low pass because low frequencies are passed through the system. So this system is a low pass system, basically. So viewing transfer functions or dynamic systems in terms of the frequency domain point of view, you can see that, of course, this is a low pass. And if I'm not mistaken, I can just change it into a high pass one, hopefully. Let me just adjust it a little bit. Let's run it again. Yeah, it's not a high pass one. It is a band pass filter at this point. And if we have omega equals 1, again, it should be just passing through the system as it is. Yep, you can see, but all the other ones are attenuated, basically almost rejected. It has a certain quality factor, etc., etc. It's more about the frequency domain data at this point. But you can see that the Bode plot can help you out in understanding systems in a wide range of frequencies. It is an important one. And in the control system design lecture, we will be using the Bode plot in order to even design controllers. So it's quite important. And it is also important to know that it has a connection to the Fourier transform. It can be generated by just directly plugging in S equals j omega and varying omega over an interval and just plotting the polar coordinates results. And it is also important that basically applying a certain sign with that frequency, reading the gain and phase data will help you out in determining the output. So The last but not least example, this is a quick one, so let's get through that one and our today's discussion here. Let's assume that we are using the control system toolbox and we will be using the step function here. But what about the other types of inputs like impulse and ramp? You can go ahead and use LSIM here, because if you provide u equals 1 all the time, this would correspond to step response. If you apply 1 once and zeros then, this would sort of replicate the impulse response. Of course, this is not ideal, but this is the best we can get close here. And if you use u equals t, that would be unit ramp. Of course, if we talk about step, impulse, and ramp, we're talking about unit step input, unit impulse input, and unit ramp input. So you can just use these three types of inputs and LSIM in order to generate the corresponding plot that you're interested in. And coding a more mathematical representation into this is also possible, and you can apply it with LSIM. But I'm more interested in a certain property that we will see at the end of this question here, and that it is actually more, even simpler than you might think to get the step response, impulse response, and ramp response of a certain transfer function. So let's maybe borrow this transfer function here, but of course get rid of that. There we go. And let's plot the step response of this transfer function here. Now, if you use it like this, and just plot t comma y, a certain color, then a line width. Let's open up a figure. Hold on, grid on. Yeah. So this is basically the step response of this function. Now we're interested in the following. We want to get the ramp response, the impulse response, let's say impulse, let's say ramp, by sort of using the step function that is already available to us. So it's kind of interesting to ask someone to find out the impulse response or ramp response of a transfer function by using the function named step. So yeah, why can we do this? Basically, it is more about the property of GS than about the step function here. Now, alternatively, and we've talked about this as far as I remember, what we can do is we can use the symbolic toolbox. We can define sim s and t, and then use the iLaplace function here, provide GSS, or actually what we do is we provide ys, but we generate ys in terms of gs times us. And then we choose us equals 1 divided by s because we are interested in basically the step response or step type inputs. So if it's step, we choose us equals 1 divided by s, and ys is equal to gss us. In this case, it is just going to be divided by s, gss divided by s. And we take the inverse Laplace transform, which will give us yt, plug in t, plot it, and you have the response. Now, if we are interested in the impulse response, what we have to do is we have to choose u equals 1, because unit impulse, of course. If it's going to be another constant, then this would be another constant. But if us is equal to 1, we will get basically GSS on its own. So let's call this ys tilde, or yeah, ys doesn't really matter. But what I'm trying to do is I'm trying to come up with a different transfer function. So I'm going to look for tilde here in order to GS transfer function. But if I use step function to that, if I use GS tilde, it should correspond to the impulse of GS. So I'm not going to use GS, but I'm going to use another transfer function, a different one, and I hope to get the impulse response of GS rather than the step. Or in other words, the step response of GS tilde should correspond to the impulse response of GS. Now, how can I do that? Well, I'm interested in GSS. I'm going to use GSS tilde divided by S as a function. If I equate them to each other, we'll see that GSS tilde should be S times GSS. So interesting fact, if we use S times GSS instead of GS, so this corresponds to TF10 like this. Of course, GS. So we have GS. Instead of looking at that, I'm going to be looking at the step response of this one here. Now, let us first see if it's really working or not. So the step function of that, by the way, let me just go ahead and use subplot here. 3 rows, 1 column. The first of them, let's call X label time. And maybe the title should be impulse GCA. There we go. The second one, the third one, this one should be step. This one should be ramp. And there we go. Now I'm going to plot this step response on the second one. And this one should go on the first one here. By the way, let me change it to blue. So yeah. There we go. So now, if this is supposed to be the impulse response of the system, and this is the step function of the same system. Now, how can I be sure that this is the impulse response of the system, or why does this work, in fact? Well, since we are dealing with LTI systems, linear time invariant transfer functions, what I can do is I can do the following. I can take the derivative, because multiplying with S is just taking the derivative. And the derivative of the input will also be the derivative of the output. So if I apply step to it, take the derivative of that, or taking the derivative of the step response, the output will give me the impulse response. So this is only for LTI systems transfer functions. Therefore, what I can do is I can do a similar thing for the ramp response. And as you might guess, I can just do GS tilde divided by S square here. Why? Because I'm going to use 1 divided by S square for the ramp type input. So I can just, so I'm interested in GS divided by S square here, but it would be G tilde divided by S. So this would be basically the same. So here I can see that instead of taking the derivative, taking the integral will also give me the ramp response. So let me just change it here. Instead of having this, I'm going to have an integrator. So add an integral, you will get the ramp response here. So let me just show you. And what I can do is I can just basically create also the inputs, or kind of emulate that. So let's call this U equals zeros size t, but only the first one here. Of course, this is not exactly what we want, but this is kind of showing the impulse here, impulse response or impulse input. Here we can just have u equals ones of size t, because it is just going to be 1. Let's have this black and tu. And here we will have t comma tk, or we can also say u equals t and then t comma u, because it is the unit ramp function. So let us update this and see. There we go, but we didn't. So this one is basically the step. Yeah, that should be it, I guess. But now we messed up the order. The impulse response should be the first one. Step response should be the second one. There we go. Makes more sense now. Now you can see that, of course, you can use Simulink or other stuff to validate if this is correct or not. If this looks like the impulse response, you can see we have the ramp type input 2. There's a slight error in the tracking here, or they look familiar, at least. You can see that there's a slight difference, but it's not noticeable. Maybe at the beginning, it's still not really. Yeah, there's a offset here for the ramp response. We have the step type response here, and we have the impulse response. Now, what I mean to say is that if you take the integral of this blue signal here, you'll end up in this step response. And if you take the integral of that, you should end up in the ramp response. Or vice versa, what you can do is you can take the derivative of this, you will end up in the step response. Take the derivative, you will end up in the impulse response. And taking the derivative or taking the integral of a certain function is done with or via multiplying with s for derivative or dividing by s for the integral. And you can just embed this into the transfer function and you would then get the corresponding response. You can even go further and have a parabolic type input, add another integrator to that. That would be t to the power of 2, I guess. And then you would just have this as a result. And let's increase that too, because the integral of a ramp would be then t squared by that. But I guess there should be a coefficient divided by 2, because if I take the derivative, it should be equal to t. So let's increase this by 1. This is the fourth one. And x4, and we should be good to go. Now you can see that I have the parabolic input now, and you can go on like that as you wish, because the Laplace property of taking an integral, yeah, we can continue on like that. But you get the idea. You can use a single function, step function, take the derivative, take the integral, in order to come up with the impulse or ramp responses of a certain transfer function. So dealing with linear transfer functions is quite interesting if you think about it, because you can just do almost anything with it and it probably works. So this will be it for this week. You will see that there are certain mathematical things here, additional stuff. If you are curious, you can check it out. And I have actually used a band stopping or band pass filter. I don't remember. We'll see. A band pass filter that has a quality factor, a corner, low frequency corner, high frequency corner, a bandwidth, and you can see that that filter has actually a transfer function, and you can implement it for the Bode plot here, and you can see that it just passes these frequencies and stops the other frequencies, basically. There's that. There's also a nice documentation on the stuff that I've talked about just now, about the integral and derivative parts. And you can see we have kind of this response here with another transfer function, of course. So feel free to examine this. And today's topic was about the root-locus plot, Bode plot impulse. And by the way, we have used some MATLAB symbolic toolbox and control system toolbox in order to answer certain questions. This is it for this week. So see you next week in the next lesson.